Hello, welcome to another module in this massive open online course on probability and random variables for wireless communication. In the previous module, we have started looking at random processes and we have defined the mean and autocorrelation of a random process, and also we looked at a special kind of a random process, a wide sense stationary random process in which the mean is a constant, that is, it does not depend on time, and the autocorrelation depends only on the time shift, that is autocorrelation corresponding to T1 and T2 depends only on the time shift tau between T1 and T2. Let us write these definitions down again once again, that is for a wide sense stationary, that is, remember WSS is a wide sense stationary random process xt. For a wide sense stationary random process xt, we have expected value of xt, which is mu x, which is a constant, that is, this is a constant, and further we have the autocorrelation xt. So, this is basically, this is the mean, and we have the autocorrelation xt times xt plus tau, this is the autocorrelation. Remember, this is the autocorrelation which depends only on, that is, it depends only on the time shift. This depends only on time shift. Depends only on the time shift, that is tau. In fact, now if we look at this autocorrelation, if I set this time shift tau equal to 0, what we get is we get expected xt times xt plus tau, but time shift tau is 0. So, this is xt times xt, which is expected x square t, which is equal to expected x square t, which is basically rxx corresponding to the shift tau is equal to 0, and you can see this is nothing but the, this is basically the average power this is the average power in the random process xt. So, if I set this tau equals 0, what I get is autocorrelation rxx of 0 is expected xt times xt, which is expected of x square of t, and expected the average value of x square of t is nothing but the power of the random process x of t. Therefore, rxx 0 denotes the power of the average power of the random process x of t. So, this average power of the random process x of t equals rxx of 0. Let us now look at an interesting example in the context of this random process and wide sense stationarity in the context of wireless communication. Let us look at an example of a WSS, wide sense stationary random process, in the context of wireless communication. Let us consider a signal, consider our signal x of t, which is equal to alpha times cosine 2 pi f c t plus theta, correct. where alpha, what is alpha? This is our alpha is our amplitude, Fc is the carrier frequency, everyone should be familiar with this in the context of communications or wireless communication, and theta is basically the phase. So, we are considering a wireless signal xt which is equal to alpha cosine 2 pi fct plus theta, where alpha is the amplitude, fc is the carrier frequency and theta is the phase of this wireless signal. This is a very common model, this is a very common model for the wireless communication signal, or for that matter any communication, any narrowband communication signal, all right. So, now let us look further, let us incorporate randomness in this. Now, frequently what happens in such signals, frequently in a wireless signal, frequently we have in a wireless signal we have theta is random, theta the phase, that is your phase. What is theta? Remember theta is the phase, this phase is random. Further, how do we model this randomness? Theta is uniformly distributed over the interval minus pi to pi. So, what we are saying is we have the wireless communication signal alpha cosine 2 pi fct plus theta, where theta is the phase, and frequently this phase theta is random. Is random, how is it distributed? What is the probability density function? It is uniform in the interval minus pi to pi. So, it is a uniform random variable, and that random variable is given as follows, that is, if I look at this interval, minus pi comma pi, you have the magnitude of this is 1 over 2 pi. So, the probability density function f of theta equals 1 over 2 pi when minus pi is less than or equal to theta is less than pi. So, for theta, for this phase theta in the interval minus pi to pi, the probability density function is 1 over 2 pi, and outside of this interval of course this probability density function is 0. And now you can see this is a valid probability density function, because first it is greater than 0, that it outside inside this interval minus pi to pi it is 1 over 2 pi which is greater than 0, and outside of this interval it is equal to 0, therefore it is greater than or equal to 0. Further, if I look at the area under the probability density function, the area under PDF that is equal to 1 over 2 pi times 2 pi, which is basically 1. So, the probability density function is basically integrates to 1, that is the total probability is basically 1, therefore, this is a valid probability density function. Further, this is uniform, it takes the uniform value 1 over 2 pi over the entire domain, that is minus pi to pi, therefore, this is a uniform random variable. Because this is uniform over the domain, this is a uniform random variable. So, further this is a uniform random variable. So, the phase theta is distributed uniformly in pi minus pi to pi. Further, we are also given that the amplitude alpha comma carrier frequency, these are constant, that is the amplitude alpha, that is remember this is our amplitude alpha and this is the carrier frequency f c, and these are constant. Now, the question that we want to ask is this signal x t is x t wide sense stationary, that is WSS. That is, we want to ask the question, is this x of t, is this signal x of t, is this wide sense stationary, is this a random process, is this wide sense stationary. Okay. So, that is the question that we want to ask. And now, let us examine this. We are given basically x t. First observe that if we look, so let us look at the solution. We have x t equals alpha cosine 2 pi f c t plus theta, and we also have theta is random in nature, theta is a uniformly distributed random variable. Further, look at this time instant, this is a function of time. This is the function of time t, right. So, we have x t which has the phase theta which is a uniformly distributed random variable. Further, this is cosine of 2 pi f c t plus theta, therefore, it is a function of time. So, therefore, it is a random variable which is a function of time, hence x t is a random process. So, first we have established that this x t which is a random signal is in fact a random process. So, this x t, this is a random process. So, x t is a random process, it is in fact a random process. Now, let us examine if basically it is a wide sense stationary process. Let us examine if WSS, if x t is WXS. First, let us look at the mean, let us look at the expected value of x t. The expected value of x t is equal to the expected value of alpha cosine 2 pi f c t plus theta. Let us look at the mean of this random process x t, which is the expected value of x t, which is expected value of alpha cosine 2 pi f c t plus theta, which is equal to, if I look at this integral minus infinity minus pi to pi alpha cosine 2 pi f c t plus theta f of theta, that is a probability density function, multiply the function by the probability density function and integrate with respect to theta. So, how do we check if x t, if this random process x t is a wide sense stationary random process? First, remember the wide sense stationary random process is stationary in the mean, therefore, we have to check the mean. The expected value of x t is the average value of alpha cosine 2 pi f c t plus theta, which is alpha cosine 2 pi f c t plus theta multiplied by the probability density function f of theta and integrated over this domain minus pi to pi. And the probability density function is a uniform probability density function which is 1 over 2 pi. So, I am going to replace f of theta by 1 over 2 pi. Therefore, this mean is basically equal to minus pi to pi alpha divided, because this quantity here is basically 1 over 2 pi, that is f of theta cosine 2 pi f c t plus theta integrate d theta. Now, if we look at this, we have alpha over 2 pi is a constant. So, this is nothing but alpha over 2 pi sine integral of cosine 2 pi f c t plus theta is sine 2 pi f c t plus theta divided by 2 pi f c between the limits minus pi to pi. And now, for theta, if I substitute pi and minus pi, I have alpha over 2 pi times 1 over 2 pi f c times sine 2 pi f c t plus pi minus sine 2 pi f c t minus pi. This is the difference of sign between two phases separated by 2 pi. So, therefore, this is clearly equal to 0. Therefore, we have 0 equals mu x t, that is the average, which is equal to mu x, because we can see this is a 0, which is basically a constant. What is this? This is basically a constant, and this is not a function of the time t. So, what did we do? We looked at the average of this random process, which is the expected value of x t. We have computed the mean of this random process, and we have showed that expected value of x t is equal to 0, and therefore, since expected value of x t is 0, it is a constant which does not depend on the time t. Therefore, this random process is in fact stationary in the mean. It is not yet a wide sense stationary random process. Remember, because for that we have to also examine the autocorrelation, but first we have established that the mean mu x is not a function of time. Therefore, this is stationary in the mean. So, this signal x of t, the mean is not a function of time. Therefore, this is stationary the mean is not changing as a function of time. Therefore, this is stationary in the mean. Let us now look at the autocorrelation of this random process. Let us now look at the autocorrelation. Remember, the autocorrelation at two time instants x of t and x of t plus tau is expected value of x of t into x of t plus tau, which is basically the expected value of alpha cosine 2 pi f c t plus theta, of course, times alpha cosine 2 pi f c t plus tau plus theta, right. We have to look at the autocorrelation corresponding to two time instants t and t plus tau, that is time instant t and shifted by tau, that is at t plus tau. So, that is the expected value of alpha cosine 2 pi f c t plus theta times alpha cosine 2 pi f c t plus tau plus theta. Again, I am going to multiply by the probability density function of this parameter theta and integrate between the limits minus pi to pi, right, to compute the average. That is equal to, what is this equal to? This is equal to alpha square integral minus pi to pi. This is, well, this is the expected, this is cosine 2 pi f c t plus theta times cosine 2 pi f c t plus tau plus theta times f theta of theta, probability density of function of theta integrated to the theta. Now, let us look at this quantity cosine 2 pi f c t plus theta. Cosine, this is of the form cosine A, cosine B, which is basically half cosine A minus B plus cosine A plus B. Therefore, this is equal to alpha square divided by 2 minus pi to pi cosine A minus B is cosine 2 pi f c tau plus cosine A plus B, which is cosine of 4 pi f c t plus 2 pi f c tau plus theta multiplied by the probability density function f of theta. Remember, this is 1 over 2 pi. So, multiplied by 1 over 2 pi integrated, multiplied by 1 over 2 pi and integrated with respect to theta over the range minus pi to pi. And this now, if you look at this, this is alpha square divided by 2 into 1 over 2 pi. And if you look at the first term is cosine 2 pi f c tau, which is a constant, does not depend on theta. So, that comes out of the integral. So, I have cosine 2 pi f c tau times integral minus pi to pi, which is basically simply 2 pi. So, this is cosine. So, what is this going to be? This is going to be cosine 2 pi f c tau times 2 pi plus I have integral minus pi to pi cosine 4 pi f c t plus 2 pi f c tau plus theta, that is simply sine of 4 pi f c t plus 2 pi f c tau plus theta. This has to be evaluated between the limits, minus pi to pi. Again, we have the difference between two sine at the sine at two phases which are separated by 2 pi. Therefore, this is equal to 0, and what we are left with is basically we are left with alpha square over 2 1 over 2 pi times cosine 2 pi f c tau into 2 pi, and what is this equal to? This is basically equal to the 2 pi's cancel, and this is equal to alpha square over 2 cosine 2 pi f c tau. And as you can see, therefore, this is alpha square over 2 cosine 2 pi f c tau, and therefore, now you can see the autocorrelation at 2 points t and t plus tau does not depend on this time difference tau, and therefore, this is stationary in the autocorrelation, and stationary since it is stationary in the mean as well as stationary in the autocorrelation. Therefore, now you can see this does not depend on t. Therefore, it is stationary in the autocorrelation. Therefore, it is stationary in the autocorrelation and stationary in the mean. Therefore, x t equals alpha cosine 2 pi f c t plus theta, where theta is uniformly distributed, uniform in the interval minus pi to pi. This we are saying this signal, or this is a random process which is wide. This is wide. This is a wide sense stationary random process. So, we are saying x t, which is alpha cosine 2 pi f c t plus theta, where theta is a random variable uniformly distributed in minus pi to pi, the amplitude alpha and the carrier frequency fc are constants. This we are saying is a wide sense stationary random process, because the mean mu x is constant, which is 0, does not depend on the time t, and further the autocorrelation corresponding to 2 time instants t and t plus tau depends only on the time shift tau, and that is equal to alpha square divided by 2 cosine 2 pi fc tau. Okay. So, this is a wide sense stationary random process, and further now we can also see that Rxx, that is the power in the random process. Remember, we said the power in the random process Rxx0, Rxx0 is alpha square by 2 cosine 2 pi fc times 0, which is cosine 0, which is equal to 1. Therefore, the power equals alpha square divided by 2. So, the power of this random signal, so the power of this random signal or the power of the random process is equal to alpha square divided by 2. Remember, when we have a sinusoid of amplitude alpha, the power is alpha square divided by 2. However, we cannot directly compute the power that way, because this is a random signal, this is a random process, and therefore, we had to define, we proved that this is a wide sense stationary random process, we computed the autocorrelation of this, and then we derived the power of this random process as Rxx0, where Rx, that is Rxx of tau at tau is equal to 0, at the shift tau is equal to 0, that is the power of this random process xt. So, in this module we have looked at an interesting application of this interesting example of wide sense stationarity. We have seen a wireless signal which is given at alpha cosine 2 pi fct plus theta, where alpha the amplitude is constant, fc is the carrier frequency of the signal, and theta is a random phase which is uniformly distributed between minus pi to pi, and we said this signal or this random process is actually a wide sense stationary random process. And we have demonstrated that by showing that this is basically stationary in the mean and the autocorrelation, and we also derived the power of this random process as Rxx0, which is alpha square divided by 2. So, let us end this module here. We will look at other aspects of random process in the subsequent modules. Thank you very much.